All right, let's jump right into this. Welcome to this explainer, where we're going to tackle a subject that, honestly, is notorious for completely destroying exam scores. Yep, we're talking about signal processing. Look, if you've been approaching this topic purely by trying to memorize a textbook full of dense, terrifying equations, you are basically playing the game on hard mode. It doesn't have to be that way. Today, we're shifting our approach entirely. We are going to turn that dense math into core, actionable intuition.
So, you might be wondering, why is this specific subject such a massive hurdle? Why do so many incredibly smart students fail or struggle here? Well, it's because success in signal processing exams requires intuitive pattern recognition, not just staring blindly at integration and summation symbols until your eyes water. The examiners aren't just testing your calculator skills, right? They're really testing if you can look at a system or a signal and just instantly recognize its fundamental behavior.
So here's our roadmap for this explainer. We're going to start with signal foundations, move into impulse reflexes, run through the LTI systems checklist, decode convolution in Fourier, and then end by identifying some brutal, standard exam traps.
Okay, Module 1, Signal Foundations. We need to draw a hard line right away between the two foundational ways we classify how big a signal actually is.
The distinction between these two is surprisingly simple once you visualize it. You've got energy signals on one side and power signals on the other. Think of an energy signal as the total fuel burned in one single trip. It's totally finite. It's one pulse, basically like a firecracker going off. One quick bang and then just silence. A power signal, on the other hand, is an infinite, never-ending, steady fuel burn rate. Think of the 50 Hz hum from a wall socket. It literally never ends, but its rate of energy delivery is perfectly steady over time.
Now, to lock in your Tier 1 marks, you just need to memorize these exact 4 verdicts because they show up everywhere. First, the unit step is a power signal. The unit ramp? Well, because it keeps growing and its average blows up to infinity, it's neither. Third, any periodic signal is fundamentally a power signal. And finally, any finite duration pulse is always an energy signal. Pure recall of these 4 specific verdicts is going to save you from doing any 0 to infinity integrations on test day.
Oh, and let's talk about a favorite exam trap right here. Discrete time periodicity. Examiners love to give you a beautiful-looking discrete sinusoid, say, something like sine of n, and casually ask for its period. But wait, you must always run the rationality test first. A discrete sinusoid is periodic only if its frequency divided by 2 pi results in a rational fraction. Why? Because n jumps in discrete integer steps, so the samples only realign if that ratio is rational. If it's irrational, don't even calculate anything. The correct answer is just not periodic.
Moving right along to Module 2, we are looking at the unit impulse function, the infamous delta function.
My biggest piece of advice, stop treating this as complex calculus. Instead, you need to treat it as 4 instant mathematical reflexes that you memorize like your multiplication tables. Let's hit them fast. First, sifting. When you integrate a signal against an impulse, it simply reads the value of the signal at the exact location of the impulse. Second, scaling. If the time variable inside the impulse is multiplied by a, it scales the outside by 1 over the absolute value of a. Third, shift by convolution. Convolving with a shifted impulse just shifts your original signal by that exact algebraic amount. And fourth, combined. Integrating a scaled impulse against a signal just plucks out the 0 value but scales it by that absolute denominator.
Now let's focus on a highly specific trap related to that second reflex, the scaling one. When scaling the impulse function by a negative constant, examiners will explicitly use a negative a value, like asking you to evaluate an integral with delta of negative 3t. This wording exists purely to catch students who blindly write 1 over a instead of 1 over the absolute value of a. You have to always use the absolute value sign in the denominator. I highly recommend using a simple 60-second recall routine before the test to lock in these reflexes. To prove how absolutely critical this is, the 2025 exam spent 3 consecutive questions testing just these properties. That is incredibly fast scoring if you know your reflexes, and a total devastating time sink if you don't.
Okay, let's jump into Module 3, Linear Time Invariant, or LTI Systems. You should think of this module as a strict security checklist. You run this brilliant little checklist on every single system box the exam paper throws at you. 5 core properties and their instant eyeball tests. 1. Is it linear? Look for superposition, meaning no x squared, no absolute values. 2. Is it time invariant? Look for delay in equals delay out, meaning there is no stray t multiplying your input signal. 3. Is it memoryless?
The impulse response has to be just a scaled delta, nothing wider. 4. Is it causal? It must be non-anticipative, meaning the impulse response is perfectly zero for any time less than 0. And finally, 5. Is it BIBO, meaning bounded input, bounded output, stable? The impulse response must be absolutely integrable. Seriously, run this mental checklist and you won't even need to touch your scratch paper.
Now shifting over to the transform domain, we can instantly verify stability visually. For continuous systems in the S-plane, stability simply means all poles are strictly in the left half plane, period. For discrete systems in the Z-plane, stability means all poles are strictly inside the unit circle. It's a pure, instant visual check.
But, and this is a big but, watch out for this recycled false judgment they absolutely love to hide in multiple choice questions. The exam might state, the inverse of a causal system is always causal. You might be thinking, well, that sounds right. It's completely false. Disarm this trap by remembering one simple counterexample. A causal pure delay, like a system that delays a signal by 1 second, has an inverse of a pure advance. And an advance requires looking into the future, which automatically makes it non-causal.
Okay, let's power through to Module 4, where we take terrifying operations like convolution and Fourier transforms and break them down.
Let's start with convolution. You can actually do this graphically without any tiers. Picture your two signals as little paper strips. You simply take one strip, flip it horizontally, slide it across the other strip, and at every single position, you multiply the overlapping areas and integrate to find the total area. Flip, slide, multiply, integrate. The exam rarely asks for massive, long integrals. It usually just asks for standard results using this exact graphical logic.
And when we hit Fourier series, we inevitably encounter the Gibbs phenomenon. Trunking a Fourier series causes an overshoot of about 9% right next to any jump discontinuity. Now, here is the exact secret the distractors prey on. You might think adding more harmonics fixes it. Adding more harmonics does squeeze that wiggle to make it narrower, sure, but that 9% height, it never dies. It literally never shrinks. Remember that fact. I want to give you a few more Fourier hacks for guaranteed free points. First, real sequences guarantee conjugate symmetric spectra, meaning the magnitude is perfectly even and the phase is perfectly odd. You can often just mirror your answers without doing a shred of computation. Also, remember the sinc function is an even function with zeros at every single integer. And what about your power spectral density, or PSD? It must always be real, even, and non-negative. If a multiple choice option violates any of these, just cross it out immediately.
Finally, welcome to the boss battle, Module 5. We are explicitly identifying the top traps and distractors that are purposely designed to steal your marks in those frantic final minutes of your exam.
Take this exact trap pulled straight from the 2025 paper. They wrote an otherwise flawlessly perfect statement about stability, but they flipped just one tiny word, saying poles lie in the right half plane instead of the left half plane. One flipped word makes the entire statement absolutely false. In these statement questions, you must actively scan for these flip points, left versus right, inside versus outside, includes versus excludes.
Here is another incredibly tricky one that catches everyone. We're generally taught that finite impulse response, or FIR filters, are inherently non-recursive, right? So when the exam casually says, efficient realizations of FIR filters exist as both recursive and non-recursive structures, your gut reflex is to mark it false. Don't do it. Frequency sampling realizations are actually recursive implementations of FIR filters. Precision of wording absolutely wins marks here.
Which really brings us to our golden rule of exam survival for this subject: intuition over memorization. If you run your system security checklist, if you spot those one-word false flags, and if you rely on pattern recognition over blind math, you are going to secure your Tier 1 marks with time to spare. Structured logic is your ultimate weapon.
So, I leave you with this final challenge. Are you ready to apply the rationality test, verify your impulse reflexes, and scan for those sneaky flip words on your very next practice paper? I bet you are. Grab the cheat sheets from the links below, start testing these mental frameworks today, and take complete control of your signal processing scores. Thanks so much for joining me on this explainer, and happy studying. You've got this.